we try to find out how can we recover the message that has been modulated from the modulated signals. By that we mean how do we perform the demodulation. And we see that the demodulation of an FM signal requires a system that produces an output proportional to the instantaneous frequency deviation of the input signal. And such a system is called frequency discriminator. And if the input to the frequency to the ideal discriminator is an angle modulated signal that is defined as such, then what we expect from the discriminator is that y of d, the output at the discriminator, should be a function of the derivative of the phase component of the modulated signal and multiplied by with the sensitivity of the discriminator, and that sensitivity is the one that we are defining as KD. So for an FM, of course, we know we already have two versions, FM or PM. For FM to start with, we say that consider that phi of t is given by equation 48, which we had said earlier that phi of t is always given by omega c of t plus, oh sorry, I think that is what we had already said earlier, so this is not the case. We had said that phi of t for FM is given by kf minus integral of from minus infinity to t m of lambda d lambda. This is how we defined the phase dependence of the frequency component as defined for FM. So if that be the case, then the equation 430 that we have defined here, which is equation 430, then we say that is going to be given by yd will be, when you differentiate this with respect to t, say d dt on both sides, we are going to end up with kd remains there, then kf is still there, and then when you differentiate an integral, you are left with this goes and this goes, we are left with mt. So this is what we get as equation 431. And we now see that the characteristics of an ideal discriminator are shown in this figure 4.6, whereby we are saying that the characteristics, which is a function of yd of t, is going to be a straight line that is defined by having a slope of kd and of course varying with respect to the angular frequency of the input signal omega c. And now we can also observe that the frequency discriminator can also be used to demodulate the PM signals. So of course, ideally it should work for the FM, but we are saying that it is possible to understand the relationship between the FM and PM, and we see that we can be able to demodulate the PM signals using the frequency discriminator. And how do we do that? We say that for PM, we know that phi of t is given by equation 4.6, which we said that phi of t is given by kp directly related to the message signal itself, which with the constant of proportionality being kp. And from what we have seen, we can define yd to be given by kd multiplied with the change in message signal with time. Of course, the first derivative of message, because we have said that we define that y of d should always be given by this equation. So this is how we defined equation 430, that the ideal discriminator should have a constant of proportionality being defined as the sensitivity of the discriminator, and then you differentiate the phi of t with respect to time. And therefore, since we have defined phi of t to be this, then when you differentiate both sides with respect to time, you end up with kp dm of t d dt. Therefore, this is now the output from the discriminator or the frequency discriminator that now is able to relate the phase of a PM modulated signal with respect to the message that was sent. So clearly, because our objective is to discover the message signal empty, and we have obtained the derivative of empty, what we are saying therefore is that if we differentiate, if we integrate the output of the discriminator with respect to time, then we are going to be able to get empty from this output here. So having observed that we can perform integration of the discriminator output to yield the output that we require, which is that of MT, then we say that a demodulator for PM can therefore be implemented using the FM demodulator followed by an integrator. Now we want to see how we may achieve the simple or ideal discriminator, and we have a simple approximation of an ideal discriminator that is achieved using an ideal differentiator followed by an envelope detector. This is seen in this figure. What we are saying is that we consider an input to the differentiator that is defined as xc of t, so that at the end of the output of the differentiator, we will have x prime of t, x prime c of t, which is defined in equation 443, which is a straightforward differentiation. And therefore, when we follow this with the envelope detector, what we are saying is that this detector will observe will detect the amplitude changes that is resulting from the derivative or the output of the differentiator, which is this term. Therefore, it is able to observe to detect the envelope of this amplitude, which is defined as this. So what we observe from this output, which is the first derivative of the input to the modulator or the differentiator for these purposes, then we observe that it is both amplitude and ergo modulated, because this term here, the one that is brought down here, is the envelope of our the x prime c of t. And therefore, we can be able to detect or like remove, which is the best word to get. We can be able to detect the message signal from this envelope here, because we are able to we can get that the phi of t is the one that is varying with message, and therefore we can be able to integrate it to get our message signal. So that is one that we observe that the output from the differentiator is both amplitude and ergo modulated. And therefore, we also know that it is ergo modulated because this term is a function of mt, and because we said phi of t is a function of mt, depending on whether it is PM or FM. Therefore, the output of the envelope detector is simply going to be omega I, and we defined omega I as this term. If you remember, we defined omega I, the instantaneous angular frequency of your modulated wave, as that. So definitely that is what is the envelope of the detector that we have, and we call that when we refer to it as the instantaneous frequency of your input signal to the modulator, which is of course the output of your modulation process.